So the remainder of this chapter is kind of like drinking water out of a fire hose. There's a lot of information. So what I intend to do, hopefully, is sort of make it interesting, but also to sort of distill things down in a way that it makes sense. So to start with, we're going to be looking at crystalline solids. And when we look at crystalline solids, we sort of subcategorize them in many different ways. I don't necessarily agree with the categorizations, but we have molecular solids. This one makes sense. These are molecules, so like water, and they're just held together by weak intermolecular forces, like dispersion forces, dipole-dipole, and hydrogen bonding. So we have individual units of molecules held together by intermolecular forces. And then we have ionic solids. Now, ionic solids are held together much more strongly because what holds them together is ionic bonds, and they form crystal structures similar sort of to the crystal structures that we've been looking at in this previous section, the cubic and the hexagonal crystal structures. And then there's the atomic solids, and this is kind of like a garbage can of information. It's just a lot of different kinds of materials. There's the non-bonding atomic solids, and the only thing that these things have in common is that they're not ionic and they're not molecular, but they're held together. They're atoms held together by weak intermolecular forces, or they could be atoms held together by other types of bonds, like metallic bonds and covalent bonds. So let's go ahead and talk a little bit about each one of these. I'll spend a little bit of time talking about molecular solids, a little more time talking about molecular solids, simply because we don't discuss it much later. So in a molecular solids, we have things like water, carbon dioxide, like dry ice would be an example of a molecular solid. And they're held together by intermolecular forces. So again, those are hydrogen bonding. That's the strongest of them, right? And dipole-dipole, and then dispersion. And because intermolecular forces in terms of relative to covalent bonds are relatively weak, they have relatively low melting points because it's easy sort of to break the solid up into the liquid. The other thing that's kind of interesting about molecular solids is their melting points are dependent on their shape. And because when you have to, for example, take benzene, it's got a very regular hexagonal shape with hydrogens all the way around. If you think about packing these, right, you think about like packing like dishes, it's relatively easy to stack them up and to get a crystal structure out of them. So it actually has a melting point of around 5.5 degrees Celsius. So it's actually a little bit higher than water. But then if you look at toluene, toluene has one CH3 group out here. It's a little bit heavier, so it has a slightly higher dispersion force. But you notice its melting point is minus 95 degrees Celsius. And the reason it has such a low melting point is it's very hard. Imagine having a dish that has pieces sticking off of its sides, and you're trying to stack these in an organized way just by lowering the temperature, and they just don't stack well. And we see this for like lipids, like fats and oils. Their melting points are really determined a lot by their intermolecular forces, of course, and their shape. It turns out, for example, if you're looking at lipids that have odd numbers of carbons and even number of carbons, they're actually trends based on whether or not it has odds or even numbers of carbons, because it turns out even ones are easier to pack together, and odd ones always have an odd number sticking out. It's a little bit harder to pack, and so there's a several degree difference in their melting point as they melt. Okay, so another interesting thing about molecular solids is that they can form, or they commonly form, what are called polymorphs. And the book gives an example of chocolate. So right? It says crystalline forms of cocoa butter. But really what they're talking about is the making of chocolate. And so if you've ever had a piece of chocolate and you store it in the fridge and then you take it out and then you look at it, it's white, right? And it's hard and it doesn't taste good, right? Well, the chemical composition actually hasn't changed. What's changed is the crystal structure. And so this is what we refer to as a polymorph. It's the same material, just a different crystal structure. And when you know how when you try to eat that chocolate, it's hard and waxy and doesn't dissolve well and doesn't taste good. Well, that's an indication that it actually has a higher melting point than like the chocolate when you put it away. So there are 7 or 6 polymorphs listed here, but I think there's several more. And what they do is they list, right, the different properties and the different melting points of each of the different crystalline forms. So when people are making chocolate, one of the things they try to control very carefully is the temperature so that they get the right crystal structure so the chocolate has the right smoothness and melting ability as you eat it. Now, it turns out polymorphism in crystals, like polymorphism is a general term. That's if you're taking biology, right? They talk about polymorphism. But this is just for the crystal structure, so that's not a related topic. But polymorphism in chemistry has really started to be studied more intensely in the last 20 years. From 2005 to 2015, there were 20,000 articles on just polymorphism in crystals. And it turns out polymorphs can be made pretty easily, and because of their different properties, people have taken a lot of interest in them. One of the areas that's an active area of research is in drug pharmacology. If you want a drug to dissolve faster, what you can do is you can look at the solubilities and the dissolving rates of the different polymorphs. Now, it also turns out that polymorphs are easy to make. So if you take, let's say, a drug and you dissolve it in one type of liquid, like solvent, right? And you evaporate the solvent to make the solid, you might get one crystal structure, and you could just change the solvent and evaporate it and get a different crystal structure. And so you can control the drug pharmacology in some fashion just by changing which polymorph gets used in the production of the drug. And they even do things like grinding the solid while they're evaporating solvent, and they end up with, again, different crystal structures which have different and distinct properties. So that's one area, is in drug pharmacology. The other area actually turns out to be in biochemistry. And enzymes turn out to have polymorphs, and you can actually have polymorphs of one enzyme distributed within one organism, and each polymorph has a slightly different property or behavior with a different substrate. So one of the active areas of research is cytochrome P450, because it is involved in the metabolism of something like 30 different therapeutic agents, drugs. And the result is, if you can decide which polymorph you're dealing with, you can helps you to tailor like what the biochemistry is that's going on with that enzyme. Well, ionic solids are made out of ions, and they have very high melting points because what's holding them together is ionic bonds. There are some interesting details about ionic structures that we'll talk about more later. But you have to think about when you're making ionic solids, we're going to try to put them into some of the same crystal structures that we've looked at before, like face-centered cubic or body-centered or simple cubic unit cells. And the thing that has to be true when you're making ionic compounds, in addition to having to get the formula right, because you have two different like ions right in the structure, you also have to get the charges right. And so this actually limits the number of structures that are available. And we'll show some of these. I have them at the bottom of the slide here, but we'll talk about them more later. But ionic solids have very high melting points as a result of being held together by ionic bonds. So right now we're at the non-bonding atomic solids. And so what are non-bonding atomic solids? They're just atoms, okay? So not metal atoms, but other kinds of atoms. So for example, xenon would be an example of a non-bonding atomic solid. Iron would be an example of a metallic bonding solid, and we'll talk more about that on the next slide, actually. And then silicon dioxide is an atomic solid that's part of what's called a network solid. Okay, so non-bonding atomic solids are held together by just weak dispersion forces, and that what they'll tend to do is form a solid that gives them the highest coordination number and minimizes the distance between the atoms, right? So face-centered cubic, for example, would be an example of a type of a type of crystal structure would sort of satisfy those kind of criteria. They have really low melting points because really all that holds them together is dispersion forces. And like we studied before, as you increase the strength of the dispersion force, you can increase the melting point of the solid. So argon melts at minus 189 degrees Celsius, and xenon melts at negative 112 degrees Celsius. So a little bit higher. I mean, both of these are really cold, but remember, argon is on the periodic table smaller or at a higher period than xenon. So metallic atomic solids are metal atoms held together by metallic bonds, and I'll explain to you what that is in a second. But these generally, like non-bonding atomic solids, try to maximize interaction between the atoms. The bonds are not directional. That is, when the atomic solid forms the metallic bonds, these bonds spread out over all of the atoms in the structure. Melting point really varies a lot with metallic solids. Generally speaking, towards the middle of the periodic table, middle of the transition elements, is where we have the highest melting points. And the lowest melting points tend to be towards the left of the periodic table. Some examples they give here are nickel or zinc. Right? This is a sort of a face-centered or body-centered cubic arrangement with atoms in the faces. Anyways, there's different kinds of arrangements, and the idea of metallic solids is they try to get as close as possible to each other as they can. Now, the way a metallic bond forms, you have to go back to molecular orbital theory. So you might recall from doing molecular orbital theory, if we took, and we did lithium, we have two lithium atoms, and for example, we're trying to look at the molecular orbitals that are created from two lithium atoms, right? And we have one electron here and one electron here. And what ends up happening is we get a constructive interaction that brings a bonding molecular orbital. That's where the electrons will drop into. So for example, these will both fall down into here. We also create an antibonding orbital. And if you remember, when we did p orbitals, right, we had a very similar situation, but in the p orbitals, what did we get, right? We had 3 coming in from one side, we had 3 coming in from another side, right? And the pattern that we got was 1, 2, 2, and 1. And all these are antibonding and all these are bonding. And you'll notice how what happens is this volume in between here is filled by the molecular orbitals created by the interactions of these different orbitals. Now, what happens, right, when you have metallic bonding, and that's what we're talking about here now, is you have not just 2, but you have like millions and billions of lithium atoms bonding together. Now let's try to just think, because uh, we're thinking in like basically linear dimensions, 2 dimensions, really 1 dimension. We're only thinking about 2 atoms side by side, but a metallic solid, the bonding is non-directional, so it's everywhere around the atom. But if we just think linear, right? If you have lots and lots of lithium atoms, like let's say you have hundreds, right, of these things, dot, dot, dot. What you end up with is hundreds of molecular orbitals, and they're very closely spaced from the top energy, right? There's some high top energy level there, and then those hundreds will be correspondingly, right, mirrored by orbitals down below. So we're just doing it in 1 dimension. The reason we had that funny stuff going on with the p orbitals is we're actually thinking in 3 dimensions when we're doing that. So what we have actually is we have a whole bunch of electrons down here. Every single one of these atoms contributes an electron to the valence band, because those are the valence electrons. And this area up here is known as the conduction band. Let me spell it out over here. Okay, so how does an electron, so now we're thinking about a metal, right? Now we're thinking about, and I'm going to make you think about a wire, right? How do electrons actually move from one end of the wire to the other end of the wire? The valence band is completely full, and it's occupied with electrons that aren't moving. They're around the atoms, and they're freely shared. But they actually aren't moving in the sense that we want to think about them in terms of electrical conductivity. What actually happens is you can get an electron to go from the valence band here, okay. Oops, that was supposed to be a laser pointer, it didn't work. You can get one going from the valence band here up in this conduction band, and then it can move freely to the left or the right. Physicists like to think about the hole that's left behind. In some situations, it's the hole that moves. We'll talk about this electron being up here as chemists, and we'll think about the electron moving in the conduction band. So the energy difference here between the valence band and the conduction band for most metals is really small, which is why they conduct electricity very easily, because thermal energy, just the room temperature energy, allows them to be promoted to that conduction band, and then they can move freely through the available orbitals of the antibonding orbitals and conduct electricity through there. So metallic bonding, right? We talk about it up to this point sort of as a general generic thing, is really a result of many molecular orbitals that are created from the many molecular atomic orbitals that are making up the metal. And then what happens is these electrons that go up into the conduction band are freely shared amongst all the atoms within the metallic solid. Now, like I said, metallic bonding strength, right, is variable. Oh, I don't know where I said it. Maybe I said it somewhere else. Metallic bonding strength is pretty variable, and so there's a lot of different melting points you can get. But in general, metals are conductive because there's very little difference between the valence, in terms of energy, between the valence band and the conduction band. So next what we have is, we've covered molecular solids, ionic solids, non-bonding, and metallic atomic solids, and now all we have left in our overview is network covalent solids. And network covalent solids are those held together by covalent bonds. So when we talked about graphene, for example, that's an example of a network covalent solid. It's a form of graphite where all the carbons in a layer are connected by covalent bonds. And then we'll look at diamond as well in a little bit. and silicon dioxide, which is the basic material for glass or sand. Crystal structures are limited by geometric constraints of the covalent bonds, so they can't form closest packed structures because elements like carbon, for example, can't make 6 or 12 bonds. Carbon can make at most 4 bonds, and that's the structure that we see in diamond. Because they're connected by covalent bonds, and they're a network of bonds, that is, the entire, let's say you took a look at a piece of diamond. If it was a perfect piece of diamond, all the atoms would be somehow connected to each other through covalent bonds. So they have very high melting points and are also very, very hard because of that. So next what we're going to be doing is taking a closer look at the structures of ionic solids. When you have ionic solids, one of the things, unlike, let's say, atomic solids, that you have to deal with, you also have to deal with charges of ions, the ratios of atoms, and also the size of the ions. Because remember, cations and anions in an ionic compound can be of various different sizes because of the loss and gain of electrons. Overall, unit cells have to have charge balance. That is, they have to be neutral. So if you have, for example, calcium chloride, calcium's got a 2+ charge and chloride has a 1- charge. So you have to accommodate in every unit cell a calcium ion and 2 chloride ions overall to maintain charge neutrality. Now, the coordination number, because ionic bonds, unlike covalent bonds, covalent bonds are limited by the number of bonds an atom can make, but ionic bonds are really only limited by the number of contacts they can make. So, in general, large coordination numbers make the unit cell more stable, but that's going to be sort of modified by the need to balance charge and the sizes of the ions. The more similar in size the ions are, the more likely they will be to have high coordination numbers because it's easy to pack them in around each other. When the sizes get really different, then it gets hard to put them next to each other in a way that balances both charge and the sort of the contact or the coordination number of the molecule or the compound. So what we're going to do first is we're going to look to see, let me say it like this. The way we sort of break down the ionic solids is first we just think about ionic solids where the charges are the same. For example, cesium's a group 1 metal and chloride is a halogen, so they're +1, -1. So that makes it easy to do the charge balance. You have to have one of each. The other thing that we do to help us understand sort of the different kinds of structures that we have is we look at the relative size of the ions. So in cesium chloride, the cesium ion and the chloride ion have similar size, and what they take is a bodied centered arrangement. Now, I just wanted to show you this really quickly to show you how charge balances. You'll notice that there are chloride ions at the corners of each corner of the unit cell, and there's 8 of them, right? So I have 8 negative charges, but how many chloride ions are actually in the unit cell? Well, there are 8 corners, but only 1/8 of an atom is in each corner, right? So what we end up with is one atom in total, one Cl atom in total in this unit cell. The Cl atom has a -1 charge. The cesium is entirely in the unit cell, so that has a total of 2 atoms in the unit cell. Right? I have a coordination number of 8, but overall we get a charge, the charge equal to 0. That is, we satisfy the criteria that the unit cell has a neutral charge. Another ionic compound that has this same structure is calcium sulfide. So you would have one calcium ion in the middle, even though it has a +2 charge, right? And then you'd have one sulfide ion at each of the corners of the unit cell. In total, though, they would still only give a -2 total charge. So ions of similar size, similar charge, right? We get a body-centered arrangement. Coordination number is 8. Now, when we look at sodium chloride, like table salt, for example, what happens is the sodium ions are a lot smaller than the chloride ions. The problem with that is then what we have to do is we have to figure out how to space this out correctly. And space it out correctly so that, one, the charges are balanced, right? And two, we get an equal number of sodiums and chlorides in the unit cell. So what I wanted to show you is how the charge balances in the sodium chloride unit cell. Now, this is a type of face-centered unit cell, but you notice the unit cell looks a little bit more complicated than the face-centered that we showed before. If you focus just on the green chloride ions, that's the face-centered arrangement with the chloride. But because you have to have sodiums in there to balance the charge, the sodiums end up going in between the chloride ions. So the coordination number, ideally for face-centered, the coordination number is 12. But for face-centered with different sized ions, right, the sodium ion in the middle here only makes contact with 1, 2, 3, 4. Let's see, 1, 2, 3, 4, 5, and 6, this guy down here. So in order for the charge to be balanced, right, we have to have the same number of chlorides in the unit cell as we have sodiums. So if we're just looking at chloride and its face-centered arrangement, you remember for the CLs, each face has 1/2 an atom in it. So I have 1/2 an atom per face, and there are actually 6 faces, right, like a die. So that gives me 3. And then I have the corners, and each corner represents an 1/8. So I have an 1/8 of the atom times 8, because there's 8 corners. That leaves me with 1, and so that gives me a total of 4 atoms of a negative charge. And so that's the same calculation we did for the sort of this simple cubic unit cells, the face-centered cubic unit cell, Now we have to count the sodiums, and so we actually have to do a little bit of extra thinking about this because we haven't talked about edge atoms yet. But if you think about, you're looking at an edge, let's say from the top, it would look like a cross, and the atom is like this. So this represents 1/4 of an atom. So these guys, for example, represent 1/4 of an atom in the unit cell. Now, if you count the edges, right, there's 1, 2, 3, 4 at the top, and then let's see, where do we have the next? Yeah, we have 1, 2, 3, 4 in the middle. You notice they twisted, and then we have 1, 2, 3, 4. So this is the same arrangement as the top. Right? So how many do we have? We have a total of 12. So we have 12 corner atoms or edge atoms. So this is for sodium. There's 12, each one being in 1/4 of the unit cell. So 12 times 1/4, that should be 3 atoms. And then the trick here is that we also have one dead center that's entirely in the unit cell. So it's like a bodied center again, arrangement, where you have one just sitting in the middle. So we have 1 atom in the center times 1. That's 1 atom. And that gives me 4 atoms in this unit cell for sodium chloride that have a positive charge. And so we have the sodium ions charge and the chloride ion charge balancing, and we also have sort of this face-centered cubic arrangement modified because you have to have charge balance, and the sodium ions and the chloride ions are very different in size from each other. So when the sizes get to be really different, and classically what this is studied with is a ZNS, zinc sulfide, which is known as zinc blend. And so this is actually known as the zinc blend structure. And they'll talk about this zinc blend structure, even though it's not zinc blend necessarily they're referring to. But it's when the charges are the same and the ion sizes are really different. This is a type of arrangement that is created. So what you end up getting is sort of a face-centered arrangement again. That is, you have atoms at the corners, and this sulfur is in this face, and this one is in the face to the left. There's one in front pointing towards you, one in the back, in the face in the back, and there's one over here. So the sulfurs are the face-centered arrangement, and then what happens is, if you remember in the face-centered cubic arrangement, we can create a structure that has tetrahedral holes in it. We talked about this when we were talking about hexagonal packing structures. In those tetrahedral holes, that's where the zinc 2+ will sit. Zinc 2+ being a lot smaller than the sulfur fits in the pocket that's in between. Well, because it sits in these pockets, the coordination number in this particular structure is only 4. Again, ideally it wants to be in this sort of much higher coordination number, ideally 12. But as we make the sizes of the ions really different, then what ends up happening is they have to accept these lower coordination numbers in order to fit together. Well, and also I should point out that zinc sulfide is actually reasonably soft for a solid. You can just sort of crack it in your fingers if you really wanted to. Okay, anyways, we could also go through this exercise of calculating the total number of charges, right? But when you do that, and I'm not going to do it, but I'll let you do it if you want to. The zincs are all on the inside of the unit cell. So there's a total of 8 charges, positive charges in the middle. And then when you count up the atoms in the corner and the faces, what you'll find out that there's a total of 8 negative charges as well. In other words, there's 4 atoms of 2+ and 4 atoms of 2- in the unit cell. So the next structure to look at is calcium fluoride. Calcium fluoride makes this what's called a fluorite structure. And this happens when you have ions similar in size, but they have different charges. So what the unit cell has to do then is it has to balance the 2-to-1 ratio or 1-to-2 ratio for cation to anion, and it creates a face-centered structure again, right, with fluorides in the holes between the calcium ions. So in order for this structure to work, and you can verify this again on your own. Remember, in a face-centered structure, the calciums are in the corner. There's 3 atoms in the faces, and then 1 on the corners, so a total of 4. What we get is an 8+ charge in total because each calcium is 2+. Now, when you look at the fluorides, all the fluorides are entirely within the unit cell. So we have 1, 2, 3, 4, 5, 6, 7, 8, a total of 8 negative charges to balance the 8 positive charges from the calcium. So that's how that unit cell works. There is also a structure called antifluoride, and antifluoride would simply be when you had 2 cations and 1 anion present in the unit cell. A compound that you might expect and does have the antifluoride structure would be something like sodium sulfide or even sodium oxide, given the 2-to-1 cation to anion ratio. And so when you make antifluoride with sodium sulfide, for example, the sodium and occupies the spaces that the fluoride would occupy, and the sulfides occupy the face-centered arrangement that calcium is taking in this image. So when you're thinking about kinds of things that you need to be able to do with this information, one of the general tasks is trying to figure out what crystal structures ionic compounds might take. So this is kind of a summary slide of how you do that. And the first thing that you do is you consider ion size and charge. So if the relative ion sizes are the same, it'll take the highest coordination number it can get, which turns out to be that body-centered arrangement with a coordination number of 8. And this is assuming of equal charge, right? Ions of equal charge. If they're very different sizes, then we assume that it'll take a face-centered arrangement. The coordination number will be 6. And then when they're really different sizes, then what happens is the ions have to fit within the tetrahedral pockets that are left by the other ions. And so what we end up with is a coordination of number 4. Again, it's a face-centered, so these are both face-centered, with one of the ions sitting in that face-centered pocket, or in the tetrahedral pocket that's created by 4 other ions. And this was what we called the zinc blend structure. And then when we have charge ratios of 1 to 2 for the cation to anion, that's when we get fluorite, and if it's 2 to 1, it's the antifluoride structure. But again, it's face-centered with a coordination number of 4. So here's a sample problems from the conceptual connection 13.3. Which compound is most likely to crystallize in the zinc blend structure? So our zinc blend structure was for ions with the same charge, and the sizes were really different, right? So if you look at rubidium chloride, they're different, but they're not that different, right? Zinc blend has to be really a large difference. Magnesium chloride is more like the fluoride structure. We have a large difference in size, right? But what you have is a 2 to 1 charge ratio. And then copper iodide has a large difference in size and a 1 to 1 ratio in the charges. So the most likely structure to take on a zinc blend structure would be copper iodide.